Okay, so in this video, we're going to start chapter 3. Chapter 3 is functions and their graphs. Okay, functions and their graphs. The first section, 3.1, we discuss functions. Okay, so first, before we discuss functions, let's talk about another concept. We call it a relation. A relation is a correspondence between two sets. Okay, so if x and y are two elements in these sets, and if a relation exists between x and y, we say that x corresponds to y, or that y depends on x. Okay, and we write an arrow from x to y. Okay, so x corresponds to y, y depends on x, and you have this arrow. And this x, we call it input. And the y is called the output. And sometimes you can say a mapping. Okay, so that's the following thing. So let's say here example. This example is more complex. Let's try to make it clear. So there's a list of the states. So Alaska, Arizona, and California, Colorado, Florida, and North Dakota, okay, so there's a list of the states, some states, and there's a number of representative in the House of the Representative. So the number of representative of representatives, it depends on the population of the state. So you have 1, 7, 8, 25, and 53, some numbers. And based on the facts, I mean, you can check it on the internet. The number of representatives will be Alaska and North Dakota. They have only 1 representative. And Arizona, you have 8 representatives. And California, and 53 representatives. And Colorado, 7 representatives. Whatever. Florida, 25 representatives. So this is a mapping. It gives you the relation between the states and the number of the representative. Okay? So a map illustrates a relation by using a set of input and drawing arrows to the corresponding elements in the set of output. So this is a map. This is a map. Okay, in the map part, ordered pair can be used to represent. Okay, you see here the relation we write this way from x to y. X corresponds to y, y depends on x. And the ordered pair, we can use this x comma y with a parenthesis. It means x corresponds to y, y depends on x. Okay, that's all. Just the concepts, We still don't have function yet. So we have relation. So you have one point, you get another point. Okay, so let's draw another map. For example, there are certain persons. For example, person. There's Dan, Gizmo, and Colin, and Phoebe, and the phone number. So we have 555, whatever number, 2345, and 594, 402, and 930, 3956, 555, 8294, and 839 9013. And the Dan has a phone number, this one. Gizmo has a phone number, this one. And Colin, for certain reason, possibly Colin is he or she. Colin has a business phone and the private phone, so Colin has two phone numbers. And Phoebe has one phone number. Okay, so this is also a map. It also represents a relation. But due to the true fact, some person can have more than one phone, so it can have more than one phone number, right? So that's the possibility. This is a relation. Calling corresponds to the phone number. The phone number depends on calling. When you get calling, you may, just say corresponds. That's my cell phone. I don't say anything else. Just say Colin has this one. It corresponds to that's the owner, and this phone depends on this depend on this person. But this is not a nice map, because from Colin you have two arrows out. So we want a special type of a relation, or we want a special type of map, so that from one input there's only one output. We do not allow multiple cell phones. That's the definition. Let X and Y be two sets. Oh, non-empty. We do not, two non-empty sets, my bad. We do not allow empty sets. A function from X to Y or into Y is a relation that associates with each element of X exactly one element in Y. So there's only one arrow from one element. So that is a function. So basically, function just means we don't like this type of a relation. One person can have only one cell phone number. You don't allow multiple cell phone number. Okay? So from one input, you cannot have multiple output. And X is called the domain of the function. X is called the domain of the function. And for each X in capital X, each element X in capital X, the corresponding element in Y, the corresponding element Y in Y is called the image or the value of the function X, or the image of X. So the corresponding element, you can call it the value of function at X, or you can call it the image of X. And the set of all images of the elements in X is called the range of the function. The range of the function. So the range of function is a set of all the images. If that point is not the image for any input, then it's not in the range. Okay? Okay. So for example, when we have certain relation, if we have a map, it's very clear if it is a function or not. For example, if we have a gas station, you put the mobile shell Sunoco and 7-Eleven, whatever, this is from other states, I guess, other city. And there's a price of the gasoline, the price of regular per gallon, whatever price. You have a 2.71, that's per gallon, 2.72, and 2.69. If your map is like this, this is a function, because from one input there's only one output arrow. There's only one arrow. This is a function. But if we have let's talk about the diamonds, carrots, it's 0.70, 0.71, 0.75, 0.78, and you have a price. It could be 1,529, 1,575, 1,767, 5, 1,798, and 1,952, whatever number. So you may have this arrow. The carrots is 0.71. It could be this price. It could also be a different price because of other reasons. So this one is not a function, because from this input you have multiple output, so it's not a function. Okay, so if you have a map, it's very obvious to determine if the map gave you a function or not. Just check if you have multiple output from a single element or not. Okay. Sometimes we don't have the map directly. For example, we have some relation. So determine whether each relation represents a function. And if it is, find the domain range. Okay, so let's see. First one, the relation. Remember, we use that ordered pair. 1, 4, 2, 5, 3, 6, 4, 7. Ordered pair. They start from the first number is input, the second number is output. We don't want this situation happen. It means from one input you have two output. From the same number in the first position you have two different second number. That is not allowed. But here the first number is 1, this is 2, this is 3, this is 4. So it is a function. There's no multiple output. It is a function. The domain is a collection of all input, 1, 2, 3, 4. The range is set of output 4, 5, 6, 7. So this is a domain range, and it is a function. And let's see the C. B is similar. C, we have a -3, 9, -2, 4 square, for example, 0, 0, 1, 1, -3, 8. So now this is not a square. Okay, now let's check. From -3 you get 9. From -3 you can get 8. So this is not a function. From one input you have multiple output. It's not a function. If it's not a function, there's no domain range. Okay? There's no domain range. Okay, so we can determine the whether a relation is a function or not based on the either map or this kind of ordered pair. And the next example, we want to determine if the equation y equal to 2x minus 5 defines y as a function of x. So we want to see if this equation really gave us a function or not. Well, the explanation will be the following. Given x, we multiply x by 2 and then subtract 5. This gives a unique element. So there's no second possible value. So it is an equation, function. This equation defines a function. This equation really defines a function. Okay. Okay, so that's not a problem. That's not a problem. So whenever you have x, you will clearly see what is y. Sometimes it's not. For example, we have x squared plus y squared equal to 1. We want to see if y is a function of x. We start from x squared plus y squared equal to 1. So y squared is is 1 minus x squared. When take square root, you will have plus or minus square root of 1 minus x squared. So given an x, there are two outputs. So this is not a function. This is not a function. Okay, so just be careful. This is not a function because given one x, you have multiple y. Okay, let's continue to find the values of a function. So here we get an equation which defines a function, and this is the equation which does not define a function. Okay. Second, find the value of function. Of a function. Normally we will use f because the word a function f, so we will use f, g, h, or maybe capital F, capital G, capital H to denote the functions. And we will say that if f is a function, then for each x in its domain, the corresponding image in the range is designated by the symbol fx. Okay, so we just use fx, f of x, to represent the image of x. Okay, and we call fx, the value of f at x, the value of f at x, that is fx, the corresponding image. Okay, be careful, fx does not mean f times x, it just means the image of x under the function f. So when we have y equal to fx equal to 2x minus 5, when we try to evaluate f of 2/3, you have to really figure out the formula. This is 2 times x minus 5, so it's 2 times, this is input, 2 times 3/2 and minus 5. 2 times 3/2 is 3. 3 minus 5 is negative 2. So f of 3/2 is equal to negative 2. Okay, so that's the meaning. And be careful, there's some remarks. The remark 1, fx can only accept numbers from its domain. Once you fix the domain, you cannot you cannot choose point outside domain to evaluate. If you do that way, you actually change the function. And second, for each input, there is exactly one output. Okay, so that's actually the definition, the importance of a function. For one input, there's only one output. And for the function y equal to fx, x is called the independent variable. Independent variable. And the y is called dependent variable. Okay, y depend on x, so x is an independent variable and the y is a dependent variable. And this independent variable sometimes is also called argument. You may see this word in some places. Okay, now let's see the example. So we always have some concepts and theorems, and then we get examples. So for the function fx equal to 2x squared minus 3x, then we're looking for f of 3. F of 3, just let x be 3. So it's 2 times 3 squared minus 3 times 3. 3 squared is 9, times 2 is 18. 3 times 3 is 9. 18 minus 9 is 18. Okay, that's all. That's it. And second, fx plus f of 3. Well, fx, this is fx. 2x squared minus 3x. F of 3, based on our computation, we know f of 3 is 9. If we didn't do this computation, you're going to do it here. So this is the sum. You just add them. So you replace it fx by this formula. Okay, and see 3 times fx. Well, this is multiplication. So it's 3 times 2x squared minus 3x. So it's 3 times 2x squared, 6x squared. 3 times 3x minus 9x. Okay, and d, f of negative x. Well, here, this is input. Whatever you have, you always put it in the corresponding position for x. So x is here, you are going to square it. So no matter what you get, you have negative x, this is input, you're going to square it. Minus 3, here is x, you're going to put negative x here. This moment, negative x is input. So negative x squared is still x squared. But negative 3x times negative x is a positive, it's plus 3x. Okay? When you have a negative sign, don't forget the parentheses, otherwise you may have a problem. Okay? That's all the evaluation. Let's say the more evaluations. E. If we have a negative fx, well, negative fx, it looks like negative 1 times fx. So you just put a negative sign. Fx is a 2x squared minus 3x. Don't forget the parentheses because fx is this difference. It's a 1 quantity. So it's negative 2x squared and plus 3x. And f of 3x. F of 3x, here, check here. You have x squared, you have input square. So whenever you have input squared, minus 3 times the input. 3x squared is 9x squared, times 2 is 18x squared. 3 times 3 is 9 minus 9x. Okay. G. F of x plus 3. Well, it will be very long. Because here you have 2 times input square. 2 times whatever inside square minus 3 times whatever inside. Okay? So this is one quantity, it's an input. You just put the position of input. So if we simplify it, it's x squared plus 6x plus 9. It's minus 3x and minus 9. 3 times x, negative 3x. 3 times 9 is 9. It's minus minus. And 2 times x squared plus 12x and plus 18 minus 3x and minus 9. So it's 2x squared, 12x minus 3x plus 9x, 18 minus 9 plus 9. Okay. The final thing, more complex. Fx plus h minus f of h over h, assume h is not 0. It's just a long computation, but it's not that bad. So you have x plus h as input. So you get 2x plus h squared minus 3x plus h. Right? Input is x, so 3 times it. Minus, because you have minus sign, don't forget the parentheses. Fh, you just get 2h squared minus 3h. Input is h, so you put h there. Okay, and then let's try to simplify it. X plus h squared is 2x squared plus 2xh plus h squared minus 3x minus 3h minus 3x minus 3h minus 2h squared and plus 3h over h. See, very just long but not difficult. Minus 3h plus 3h, they cancelled. It's continuous simplification. So 2 times x squared, 2 times 2xh, 2 times h squared, minus 3x. Minus 2h squared. Do I miss something or not? Yeah, I think I copied something from. Anyway, so far it's good, but it's not what I'm trying to compute. Okay. in the exam in the textbook it's supposed to be x, not h. So that's why I feel I couldn't finish it. So anyway, 2h squared minus 2h squared, you cancel them. So you have 2x squared plus 4xh minus 3x over h. Well, that's it. That's the best way we can do. Because I copied something wrong, so that's the best way. If I get this x correct, we can continue simplification. It doesn't matter. We try to evaluate function. Okay. And this expression, not this one, this expression, fx plus h minus fx over h. This expression, if we go through this again, let me do it quickly. Basically, it's the same steps, just change this x to be, change this h to be x. This place you cancel 3h, here you cancel 3x. Then you cancel 2x squared with 2x squared. So you have 4xh plus 2h squared minus 3h over h. This numerator, h, they all contain h, so we can factor out h. And then we cancel h from top and bottom, so we get 4x plus 2h minus 3. And this kind of expression, fx plus h minus fx over h, is called the difference quotient of f. Difference quotient of f. Okay? So if I do it correct, the formula is simpler. If I do it in this way, it's more complex. Okay, good. And next, there are many different functions. For example, if we have fx equal to x squared, then for whatever numbers we can take square, not whatever, some good numbers. So f of 1.234, just take square. 1.234 squared. By hand you can compute it's 1.522756. I'm not going to compute it, but you can try it. And if gx, another function is 1 over x, then g of 1.234 is 1 over 1.234. Well, this number is bad. You cannot write it as a finite decimal numbers. It's actually just a rational number with repeated decimal positions. H of x, square root of x. If we have a square root function, h of 1.234, possibly we can only write this way. Without a calculator, you cannot simplify it. And during the exam, we cannot use calculator. So leave this as your answer. Don't simplify it. Okay, you cannot simplify it. That's the evaluation. Sometimes the evaluation highly depends on the calculator, which you can never use. Another way. So for example, this function, this equation, 3x plus y equal to 5. We write it, we move the 3x to the right side, we get 5 minus 3x. Then this, you see how do you get the y value in terms of x? Very straightforward. This is called explicit form. And the original equation is not the a straightforward explanation about a function. So this is implicit, but it's equivalent to it. So these two things are equivalent. We simply just move 3x to the right side. You can actually move it back. So this also represents a function, but it's an implicit of a form. Okay, so you may have, for example, xy is equal to 4. Then the explicit form is y equal to 4 over x. For whenever you have x, you use 4 over x, then you get a y. But here it's implicit. Or you get x squared minus y is equal to 6. Its corresponding explicit form is x squared minus y equal to x squared minus 6. Okay, the explicit form and the implicit form. Okay. Next, how do we find the domain of function defined by certain equation? So sometimes this function does not come from some explanation. It comes from some equation. So we don't have a straightforward domain. We have to study it and figure out the domain. And in this case, the domain of f is the largest set. Is the largest set of real numbers for which fx is a real number. So it just makes sense. You can find the value. Then that input will be inside domain. So for example, if we have fx equal to x squared plus 5x, then the domain, or the natural domain, the domain is from negative infinity to positive infinity, all real numbers, the set of all real numbers. Because for whatever real number, you can take square, you can multiply it by 5, you do addition. Okay. So the domain is from negative infinity to positive infinity. And second, if your function g of x is 3x over x squared minus 4, you have a rational expression, make sure that your denominator is not equal to 0, because we cannot divide whatever number by 0. So x minus 2 cannot be 0. So x squared cannot be 4. X squared minus 4 cannot be 0. X squared cannot be 4. So x cannot be plus or minus 2. So the domain is negative infinity to 0, to negative 2, union negative 2 to positive 2, union 2 to infinity. So we just remove negative 2 and positive 2 from the number line. When we remove 2 points, you actually have 3 intervals, left, middle, and the right intervals. We use this union to glue those intervals. And be careful, we use a round bracket, because a round bracket means we do not include negative 2 and 2. Okay? H of t is square root of 4 minus 3t. Check this. In the definition of the domain, we only consider we only consider real numbers. We do not consider imaginary number. So we cannot take square root of negative numbers. So in order to make sense, square root of 4 minus 3x, 4 minus 3t. So 4 minus 3t has to be positive, non-negative. 4 minus 3t is greater than or equal to 0. Okay? 4 minus 3t is greater than or equal to 0. So it's a 4 is greater than or equal to 3t. In other words, 3t is less than or equal to 4. We divided this inequality by 3, a positive number. T is less than or equal to 4 over 3. So the domain less than, so negative infinity to 4 over 3. Because you have equal sign, this is bracket. This is the bracket. Okay? So that's the natural domain. And the third, the next example. So we have D. Fx is square root of 3x plus 11 over x minus 5. So we have to consider the numerator and the denominator both. The denominator cannot be 0. X minus 5 is not equal to 0. X is not equal to 5. This is the first case, first condition. Second condition, 3x plus 12, because it's under square root, it has to be greater than or equal to 0. So 3x is greater than or equal to negative 12. We divide it by 3. We get x is greater than or equal to negative 4. You divide inequality by a positive 3. So you keep the direction. You keep the direction, so x is greater than or equal to 4. Negative 12 over 3 is negative 4. So it's greater than or equal to negative 4, but not equal to 5. Negative 4 is here, and 5 here. You have to remove it. So the domain is negative 4 to 5, and 5 to infinity. So we use this trick to remove 5. Okay? And in this part, one x is in the domain. We say that fx is defined, is well defined, or is defined at x. Not with fx. F is defined at x, or fx exists. When x is in the domain, the function is defined at the given point, or fx exists. If x is not in the domain, we say that f is not defined at x, or fx does not exist. Fx does not exist. So, for example, we say fx, assume fx is x over x squared minus 1, then f0 exists. But f1 and f negative 1 do not exist, because when x is equal to 1, the denominator is 0. When x is negative 1, denominator is also 0. So those two things do not exist. Okay, so for example, sometimes we have this problem from the, or we have this function from the other problems. So we will have some natural requirement. Express the area of a circle as a function of its radius. Find the domain. Area. When you are given a radius, area is a pi r squared. So this is a function. The area depends on the radius by this function pi r squared. And because we're talking about geometry, you have radius. We never have negative radius. We never have zero radius. If you have a zero radius, you do not have circle, you have a point. So the domain, the natural domain, the domain is a set of all real numbers such that r is greater than 0. So you can only allow positive radius, right? Okay, so this is the first part of the section 3.1. We will continue the section 3.1 in the next video. Do your exercise. Make sure you memorize all the concepts and the definitions or names. You can relate names to the proper formulas. This is the first section. There's most of the part which is try to define certain terminologies. Okay? Okay, we will stop this video and continue in another videos. Okay, do your exercise.